So this is our CNC. We're going to take an approach that we used on the MakerBot as far as certifying people to operate it, as in be competent enough not to break it or hurt yourself in the process. So basically it's just a big Cartesian robot. X-axis is the big one, Y is this way, Z up and down. Right now for a tool head, we had a 3/4 horsepower Hitachi router. It's variable speed, and it has collects for 1/4 and 1/2 inch shaft bits. We have adapters for 3/8 and 1/8 bits. So anything that has a shaft diameter of 1/2, 3/8, 1/4, or 1/8 inch can be put in this tool. The 1/8 inch bits are kind of tiny. They have these little brass adapters with a set screw that you put in, and you put the 1/8 inch collet in the router. If you don't know what does everyone know what a collet is?
Can you pass them around?
Yes. I have one 3/8 inch one here. Basically, this is kind of a non-standard one. I probably got the wrenches and pop the ones out of this stuff.
Those are just larger versions of the ones that we use in the drill tools, right?
Yep. So if you've ever operated a drill press or something like that, or a hand drill, you know what a chuck is. It's that thing you adjust and shove your bits into. Collet is a one-size-only version of that. You can only fit in bits of a particular diameter. This is the 1/2 inch collet for this router. Basically, it's a piece of metal with a couple fins cut into it. You clamp it down and it binds really tightly with the bit you have in there, making it basically one big piece of metal. This is the 1/2 inch one. We have a 3/8 inch adapter, so you take a 3/8 inch bit, shove it in this one, shove it in this, and then using the wrenches for this router, you unscrew the 1/4 inch, you shove it in 1/8 inch, and you tighten it down tightly. Basically, when you're doing basic CNC operations, you're going to want to probably be using what's called an end mill. It's a bit. It's kind of like a drill bit, spiral, but the head of this is completely flat. And the part that actually does the cutting rather than the face is these sides. It drills down into your piece and then drags this bit through your material. This is a 1/4 inch one with a 3/8 inch shaft on it. If you go to buy these, they have a lot of different specifications. There's 2 flute and 4 flute. There's actually 1 flute. Flute means the number of spirals in the helix of the cuts. That is a 2 flute bit. This is a 4 flute. So if you look straight down it, there are 4 spirals that go up the length of this bit. They also have what are called center cutting, and I don't know what the other specification is, some other bit. If you buy these, you want center cutting. Center cutting means that there is a cutting surface all the way to the center of the bit, and if you get the other type, you won't be actually able to plunge into your material. There's no cut in that, because those bits start outside of the material and then are dragged into doing your profile, and every time that you go deeper in your Z direction, you are outside of the bit, you're in air. So these can actually be plunged into a piece of material and can be used as kind of like a flat-headed drill bit. But like I said, the part that's important are actually the flutes. These are the part that actually do the cutting on this mill.
So why would you want to have a single flute versus a...
Depending on the material that you're cutting, wood and aluminum, you probably want a multi-flute. Depends on how much material each pass takes off to.
Okay.
If you want to lop off a reasonable amount each pass, you can use a 2-flute, and more will come off every pass of the bit. And depending on the hardness of the material and how hot your bit's getting, you might use one or the other. Plastics generally use a 2-flute, or some people use 1-flute specifically for that. Because if you have multiple flutes, you're making more passes, you're taking off less material each time, and you're heating up the material because of friction.
Especially with plastic, you're going to have melting.
So yeah, if you get a 4-flute and you start digging into plastic, you're probably going to start melting things, and then you're just going to have a glob of plastic on your bit.
Do we tell the Cut2D program which
bits? Okay, getting to that.
Sorry.
So, no, that's a good transition. So, there's also end mills that have a ball end, so they're spherical on the end, and a couple other useful types of end mills. There's also these V-carve bits. So this one is a 45-degree V-carve, so it cuts a 45-degree channel in whatever you're cutting. This is a good example for signs and stuff. A lot of times they'll use a 60-degree V-carve bit. There's an interesting piece here that was actually cut on this machine that was made with a 60-degree V-carve. This is a 45 that we just cut on this a couple weeks ago. Someone wants to take a look at that.
Can you move that bag down?
So
this would have been a really tiny bit, like
that would have been an 1/8-inch bit, like a Dremel. The reason why I have 8-inch adapters is because you can get a lot of really nice tiny bits for Dremels, and that's the diameter of Dremel is. So cheap, small carving bits and things like that can be bought at 1/8-inch diameter shanks. Basically, the reason why we're going to do training for this is, unlike the MakerBot, there are consequences for running this at the end of its axis. There are also consequences for sticking your hand near any sort of surfaces that would come together. So this will hurt you, and not to mention the very fast 1,000 RPM spinning metal pieces that are going around and cutting your metal or cutting your material. This machine, if not operated correctly, will, slam right into one of its axes and, continue trying to push on it, either breaking, the parts on the axis or blowing or melting a stepper or whatever. So, never operate this without the limit switches engaged, and never operate it, basically just stick with the profiles we have set up for this. Also, keep hands clear of places where the axes come together. So, keep your hands clear of moving parts, basically. Anything moving. Wear safety glasses. Very important.
You could do safety third, but you would really not.
These, if you don't know, the parameters for your material, or just with these bits are, poorly manufactured, or any number of other things, these will bust off and then fly in a 360-degree radius and, you know, hit you in the face, the eyes, things that are being cut. Chips, things like that fly out of this thing.
So shrapnel.
Yeah, basically.
And that's bad.
That shrapnel's bad.
It can hurt. It might even
Yes.
kill you. And finding utility poles is really bad.
So, yes, safety glasses. Hands nowhere near cutting tool. Know where the stop button is. The big red scary button. This locks and stays locks. Also, if you are not near the scary button, you can know where the homing and limit switches are, so you can just tap those and stop it. So there's one conveniently up here, there's ones on the other side of the bot, there's one on the corner here, so hitting any of those will stop it. Also, do not unplug the router and plug it directly into the wall and then flip it on. There's a relay control board in the electronics box, and plug it in through that relay control. If you hit any of the stop or limit switches that stop the machine, when the router is hooked up through that relay, the router will stop automatically. So don't plug it in directly. If you see it unplugged, make sure that you have it hooked up correctly through the electronics box. That's why it's there. Basically, what this machine takes, and what the machine operates in like most CNC machines, it only takes G-code. You can't give it a 3D representation of what you're going to cut. You can't give it a drawing or anything like that and then just say cut. You have to actually do some pre-processing of whatever you're going to do. So, for instance, this was an image that was loaded into a G-code generation program. I think this was one of those, was VCarve or some other software by Vectric. There's also a good Python script out there that comes with EMC2 that you can take, feed in all of your parameters for your machine and give it an image and give it a scale for that image, as in what's the distance for a pixel. It will convert an image to a height map, and it'll also do multiple passes and smoothing passes. It'll do different scan algorithms, that kind of thing, and it will generate G-code. Once you have G-code, you load it into the G-code interpreter on this machine, which is Mach 3. There's also a open source G-code interpreter that's pretty good. It's called EMC2. And they both do the same thing. They basically take the parallel port on a PC and toggle step and direction to a stepper controller external to the PC, and they basically tell the steppers to move one direction or another, and you tell it doing the step. A stepper motor basically is a DC motor that, through charging sets of coils, can do a very precise and very exact discrete step. So basically, these motors are all 200 step per rotation motors. So that means you have to send a step pulse if you have them set up to be, one step per pulse. Basically, you have to send 200 pulses to make it rotate one time. These lead screws that actually drive the machine are 10 turn per inch, 1/2 inch Acme thread rod. So basically, you have to pulse 2,000 steps to go 1 inch on this machine. Stepper drivers can also have different modes, so you can actually have them do half step, quarter step, eighth step, some controllers 16th step. This is set up to half steps, so it's 4,000 steps per inch. what that comes down to is basically, for resolution, you have a quarter of a mil. A mil is 1/1000th of an inch. It's often used in PCB fabrication, stuff like that. So it's pretty good as far as resolution goes. So
Can we cut PCB board on this?
possibly, I don't know if there's enough, if there's too much play in this to actually cut PCBs, but I definitely want to try.
Because then we'd be able to put the drill pattern in,
Yep.
cut pattern in.
Yep. That would be something really nice for this too. There's a lot of open source software out there to do G-code generation. Not a lot of it is great. Basically, yeah, there are commercial programs that are extremely nice for doing that, but they're also extremely expensive. So most of the stuff that's going to be easy for you guys to do is going to be simple 2.5D type stuff, where you take a drawing of what you want and basically assign cutting operations to that. For instance, the CCCKC CNC logo, I basically just took an SVG of our logo that had our outlines on it, converted it to DXF, and then through a program that I purchased called Cut2D, basically took that and assigned a profiling operation. That basically means to cut out the outline of whatever you're working on. You can specify to do the cutting on the inside of the line, on the outside of the line, or on the center. So you can basically have something that's, say, you want to cut a box that's 4 inches wide by 4 inches, and you want to have a button or set of button patterns on that. You can make a 4-inch wide block and have the buttons, the diameter of the buttons you want laid out on that block in something like QCAD. If you're familiar with that CAD package, or even Inkscape, if you can get your scaling and everything right. And then you can say in your CAD software, cut on the outside of the outline of the box, so your outline is actually 4 inches by 4 inches, and cut on the inside of your buttons, so it cuts on the inside and keeps the diameter correct. There are other operations. If you want to create a region that is lower, or you want to mill the surface of something, that's called a pocket. And basically, your bit will go around the outline and then go in further and further and mill everything within a defined area or shape to a particular depth. Trying to think of any other operations. There's just some other basic operations. Drilling, you can do drilling with this. Pet drilling, or just straight on drilling if it's a material that you know is soft. Pet drilling involves the CNC going over to a particular spot, going down and backing off, going down, backing off, and creating a hole, basically, just doing a drilling operation automatically. You can mount a hand drill in this and hook it up the same way and have it do, say, a hole pattern for a speaker, or for a speaker box, or for a grill or something like that, and just have it drill a set of holes for you. So those are kind of the basic operations.
You have to switch out bits if you're going to go from
Yes.
hand mills to drilling.
You can, during operation, there's different tools you can switch out, and you can basically have a design that requires you to do some milling and then drill some precise holes.
If you had some tiny holes versus this big.
Yeah. And also you want to do things with the largest bit possible, because you'll save time and it's much less likely to go break bits. So if you can do things with a 1/4-inch bit, great. If you need the 1/8, and also, when you're doing things like pocketing or milling down a specific area, you're going to spend a lot less time with the 1/4-inch bit than an 1/8-inch bit. Plus, you'll possibly going to, or the possibility of you breaking the 1/8" bit is much greater than this. Things you need to know about to pass to your program that's going to generate your G code. You're going to need to tell it about your tool. You're going to have to tell it so it can offset the paths correctly. You're going to have to tell it if this is an in mill, if this is a V-bit, if this is a ball mill, and the diameter. You're going to need to tell it how fast to move through your material, as in, I see it generally specified in inches per minute, or in most of the software that I run through. But basically, how fast to drag the bit through your material. That's going to vary by the material and by your machine, you know, what the capabilities are. With MDF, it's pretty forgiving. You can go through it pretty quickly. The router makes pretty quick work of it, so I did this at, for instance, 40 inches per minute, and it turned out pretty well. Plastic and other things like that, you're going to have to kind of play around with it, experiment with different materials. You're going to have to hit a sweet spot where you're taking off enough material that your bit and your material doesn't heat up extensively, and you're going to have to go through slow enough that the bit can actually chew off pieces and the machine doesn't bog down. So with plastic, for instance, you either end up with melty goo on your bit, or you end up missing steps and you come up with a completed but inaccurate design, or you break, or if you're doing metal, you break the bits. So that's something you're going to have to experiment with. There's a lot of hobbyist CNC sites out there, forums. You can kind of see kind of a ballpark of where you need to be with a particular material.
So your downside of going too slow?
Heating up.
Okay.
With wood, if you've ever had a router and you tried to do routing operations, if you go too slow, the wood will start heating up. You'll start smelling it. You'll potentially burn it. With plastic, it turns to burn. So, you can, like I said, there's a window that you kind of want to be inside.
At one point, we had mentioned in previous projects that you could program in steps where it lift up the bit and wait for it to cool down. Is that something you can also do with this?
With the MakerBot and other operations, you could insert manual pauses in this if you wanted to, or just tell it to do a tool change. You can play with the actual G code too to make this do things other than cutting stuff. It's just a regular programming language.
Does G code actually specify the stepper pulse trains, or is it?
No, it specifies where you need to be and then some tooling operations.
So from 0 to 100 millimeters on the x-axis, this fast type of thing?
Kind of. I haven't looked at too much G code, like the raw stuff, but it's locations basically.
Gotcha.
Your software should be on the back side of things. You should specify the maximum acceleration and the maximum speed of your unit. So this can't go one direction and stop and then go the other direction instantaneously. It has to ramp up and ramp down because there's a lot of inertia in just all the axes. And that's actually specified in software. And one of the things you may have to adjust. I guess I should mention missing steps. So if you do something that basically causes you to miss a step, as in the motor cannot physically move the machine or the driving acme rod during that pulse, either you're going really fast one direction and it tries to pulse the other direction, and there's just too much torque, and it can't. You basically lose a step, and basically this is a closed. Basically, this is an open loop system. So whenever you miss a step, where you think you are is a little off. So if you miss a step going one direction, miss a step going back, forth, eventually when you go back to like close a loop or a circle or something, you're going to be somewhere else. So you want to make sure that you have set up the machine to have the appropriate acceleration curve. Basically, how fast can you speed up, how fast can you slow down, and maximum top speed of your machine. They all need to be reasonable. And you also need to not overdrive the machine when you're cutting material. If you drag through material too quickly, then you can miss steps and you'll be off. Missing steps is not the only thing that will put you off from where you think you are. Backlash in the system will also make your bit be a little bit off of where the machine thinks it is. So basically backlash means that you start moving in one direction, you stop, you start moving in the other direction. There's a little bit of dead space there in between when you stop and going one direction and then coming back in the other direction. It's easy to show on a whiteboard, but
who's playing with Legos?
Yeah.
Lego gears?
Yeah. Basically, if you've had a nut on a rod, if you can move the nut a little bit without turning it, that's backlash. So basically, we'll go one direction, and the threads will be on one side of the threads of the nut, and then you'll start going the other direction, and for the first a little bit of that travel, it'll actually not be moving anything. So those add up if you do a lot of back and forth operations on the machine. I've actually got a dial indicator here, so you can somewhat accurately measure the backlash and compensate for it in software. So basically, you have your nut basically have it the threads touching the far threads of the nut by either making it move in one direction, and then set this up, zero it, and then have it move back and forth, and then see how much you lost. Then you can, in software, say that I'm losing X I'm losing X distance every movement of this axis. And then you can do it on the Y-axis. The Z-axis, you don't have to really do it because you have gravity helping you. It's always going to be resting on one side of the threads of the nut. But you can have backlash in other places too, other than on your nuts that are driving your CNC setup. And you can also get nuts that specifically are designed to not allow or to allow very little backlash. This is not one of those setups. So those are things to look out for, and also things that you add feed into your program when telling it how to cut your material. So going back to telling your G-code generator how to cut something. You have to know the tool you're using and the parameters of the tool. You have to know how quickly you're going to go through your material. You need to know how deep you're going to cut in the material each pass. So you can see on some of the cut parts on this MDF, the MDF parts that were made for this were actually machined on another CNC machine. And you can see the banding at about 1/8 of an inch. So basically these parts were cut by taking off 1/8 of an inch of depth per pass. If you've got a really hard material, or something that's harder to cut, if you're trying to cut aluminum, you might take off 0.025 inches per pass. So it would take you 5 passes to get through 1/8 of an inch. basically that's another parameter you're just going to have to play with to get the right numbers for your particular type of material. And like I said, you can figure out what other people have done to try and kind of give you a starting off point. What else do you need?
Have you discovered any parameters like that so far?
Like I did for
Just
the
MDF?
Just for the MDF, I just looked that up as far as what people are using. And people's recommendations will vary wildly. So take something that you think is reasonable and use that as a starting point.
What about fixing your material and how you
Yeah.
zero out your Z?
So another important safety tip before we go on, clamp down your stuff. Clamp it down well. Another thing, when you cut through something, if you're cutting small gears or something like that, either leave little sections of material that you cut off later after you've done with the machine called tabs. You can add them in software.
To free your part instead of just
so
cutting
you
it
just
out.
basically, you cut out, so if you're, like I said, if you're cutting out little gears or something like that, add some tabs to the design, either at design time or in the software you're using. You can add tabs that are of, just thin bands of material left on your part that you have to clean off later after you've removed them from the machine, or find some way to stick that part down. Those parts will become projectiles as soon as they are cut free. I did that with some 1/8 inch acrylic on the CNC machines that we had at our high school. But yeah, as soon as they cut, as soon as you
And that's that
cut
mark
all
you
the way
see right
through-
here.
Yeah. As soon as they cut through, they will pop out and across the room, at your face.
I'll teach you.
One way you can get around that is you can put like double-sided tape underneath it. Carpet tape is good if you can get it off of whatever you're going to be pulling up. Put carpet tape down, put your material on top of that, cut all the way through, and then remove it or remove your parts later. Or some other double-sided tape, some temporary adhesive if you're not going to put tabs down.
Would you recommend, if you know that a certain part of that is not going to be cut out anymore, clamping down kind of the cutout piece,
Screwing it, or
build?
But you could halfway through the build, but I would not recommend, because some of the weird things I've seen with G-code, I would not recommend pausing during an operation manually. You can put in a pause in the G-code, like for a tool, or say that you're going to do a tool change or something like that, and then maybe clamp down another section or the other side of something. But I would generally not recommend that.
so don't screw your piece down to the bed. You try and use the clamps.
No. Or this has a sacrificial top, as in this MDF on the top here you can cut into a little bit, so you can go a little bit past your piece. But you can also put another part or another piece on top, another piece of MDF, and screw to that.
Okay.
Screw to that piece, especially if you're going to, for instance, if your piece is going to have holes in it for mounting or screw holes or something like that, cut the holes first, and then maybe just put a screw or two, through those holes to clamp it down to the piece below, and then do your full cutout. Just anything to make sure that your piece does not flow freely or just fly out of there. Also, it'll help your piece too, because it'll just be rattling around in this groove that you've cut out around it and potentially damage it if you get to the end and that part is just free and you have this very fast spinning bit just kind of in there, and your part might just sit there and wallow and get the edges cut up a little bit before the bit gets out of there.
What's the total volume of the bed?
It's about 2 feet wide by, I'm trying to think here. It's about 8 inches short of 4 feet or more, because if you're cutting, you can actually cut to out here, about that far. So it's under 4 feet in this direction, about 2 feet in this direction, and I just have to eye it, maybe less than 6 inches Z travel. It's about a quarter of a shot by, as if you had the 96-inch shot by. So you can make something like a chair or something on this, but nothing too big without making it breaking it into multiple parts.
Could we make it bigger with more pipe?
You could make it bigger with more pipe and more acting rod, quite easily. The x-axis is the easy one to extend with this. You just need some gas pipe and some threaded rod.
Can we just use it first? Can you start probing its header?
But you'd also have to build a lot more on this. The bed itself is actually a honeycomb of pieces that are cut to make it sturdy and not flex. Basically, a lot of the parts in here are ribbed and reinforced so they don't flex. Because if you have any sort of, if you put torsion on this thing and it causes it to go just a little bit, even if it was like, even an 1/8 of an inch down the entire thing, that means you're an 1/8 of an inch deeper in your material at this end than you are at this end. You need this to be flat. So it's heavily reinforced in there, so you have to add a lot more reinforcement on. Added an extra foot or two onto the end of it, or however many feet you want to add onto the end of it. Going on, what was I off
Zeroing.
on? Zeroing. Okay. This is an open loop system. When you start your piece, you kind of have to know how big your piece is. You specify it in your software, and you just know how big your cut's going to be. And you do what's called touching off, where you're going to actually go move this manually to where, like, for instance, on this piece, I set my origin for what I was cutting off up here in the corner. So I physically moved the machine manually over to that corner, set X = 0, Y = 0, and then slowly moved the tip down to the surface of this material. And then when it just touches, that's Z = 0. One thing that a lot of people will do is they'll get a sheet of paper and they'll move it back and forth, and then they'll go down a little bit and move it back and forth and go down a little bit. And as soon as that sheet of paper stops moving and just touch it with your hands, you are on the surface of the material, and that's your Z = 0.
You do that routine when you switch between milling bits and
yes. Your X and the Y are not going to change, but the height of your bit
in case
above
you
the
didn't
material,
install it the same in a way in the collet, or
yeah, the height of your bit above the material is going to change with every tool change. You will have to re-zero your Z.
You just re-zero the Z only?
Just the Z, yeah. And you can move, Mach 3 is really nice, and when you do a tool change, it'll let you move around and re-zero everything nicely. So basically, when you need to do a tool change, pick it up, move it over to someplace flat on your material, change your bits out, and then do the Z touch off again when you change bits, so it knows where the Z is.
And that can be in one G code, or should you have separate for I'm going to
for each operation?
Yeah.
No, you can just have one G code file, and there's a tool change code, and then it'll allow you to do the tool change.
Is the vertical speed different than the horizontal speed in some of those bits?
As far as
like the maximum
allowable?
you can use?
The vertical should be very low on this.
Yeah.
The cutting surface is very small.
Okay.
And the Z-axis is generally slower because you don't do that many Z-axis movements for most operations. Most of the time you're cutting out profile or something like that.
Okay.
But yeah, you can also speed up, slow down your Z-axis depending on the operation. If you're just drilling a whole bunch of holes, you don't want to go particularly. You want it to be a little bit faster. Also, you'll specify the height over the material that you pull off your Z. A lot of times in your software. Since the Z-axis is slow, if your thing is completely flat, you want to probably just have it pass close to the surface as possible because it takes longer to go up in your Z-axis. If you're carving into something or you need to make sure that you're clear of other stuff, make your Z height higher when you're traveling across your piece. Other things to do. If you're really into this and everything, you can actually have, if you have a milling machine or something like that, you have quick change tool sets where you have the all your bits that you're going to use in an operation chucked up, and you literally just put your chuck in there and tighten it down and go to the next operation. You can actually have height indexes, so like the amount of Z that you have to adjust for this bit, and then make sure that it's in there good and level and locked in, and it'll do that so you don't have to make Z adjustments every time you change out tooling, but that's if you're going to do the same setup off. Anything specific anyone wants to know about?
In the parameters of the drawing or the G code or the file, basically we have to come up with the G code and bring that to the device.
Yep.
And this device only has the CAM software for driving the machine, accepting G code and driving the machine.
Yes. We can probably get some basic stuff installed on this machine. I have a copy of Cut 2D, which is a 2.5D, which you take your paths or tools and like that, and then you convert them to G code. But there's nothing necessarily set up on this machine right now that will take a design file and generate the G code for you.
So how did you do that one? That was with DXF to...
Yeah, we did if you've seen the original, we had a marker taped to this and had it do our logo and everything. There's a program out there that's another, I believe it's another Python script that's DXF to G code that basically just takes DXF and you select your paths and you specify if you're going to cut on the inside or the outside of a particular path, your tool, and just basically all those parameters that I stated earlier, and then it's just going to trace the outline of that path in the DXF. Basically, you can't do pocketing operations with that software as far as I know. So you can't define an area and then say go to this depth at that area. It'll just go around the outside of your lines. For a lot of things, if you're just going to cut holes in something of a specific size and then cut out a piece, that is completely fine. Or if you're going to engrave something, that's completely fine as well. Because you're just going to go to a specific depth, do an outline on some specific artwork, and then you're done, basically.
I think if you cut something out with that, you'll probably need to add in the tabs in your own design.
Yeah. If you cut something out with DXF to G code, you'll have to add tabs into your design. There are some other free options out there. I haven't looked into some of the other ones that were on that thread that you originally showed me. But I guess there's two things that separate. The operation of generating your model is done in CAD software. The operation of taking your model and converting it to G code is done in CAM software. So look up CAM software specifically when you're looking for G code generation. There's a package for Windows called CAMBAM that has a free version. It has some 3D operations, it does 2D operations. The free version is a little buggy, but for a lot of people, it's pretty much all they need to get stuff done. Vectric has some cheap 2.5D software called Cut 2D that I'm using that I really like. You basically set up your material, you set up tooling paths for your different paths that you import, and it gives you live previews of your object. It automatically adds tabs to specific depths that you want in positioning, and outputs G code for a lot of different interpreters. So that's cool too. And you can always generate G code. A lot of people when we really MakerBot stuff did that. They just generated directly to G code. If you really want to, write a Python script to generate whatever you're going to generate, you can. You can also use this machine for things other than milling. One thing we were going to eventually try is to make this a foam 3D printer as a prototype. So you can actually output the G code from a MakerBot, massage it a little bit to tell it to do a tool change after every layer. Why do it about what dimensions the bed is. And you can also write encodes to do things like turn on and off relays. There's encodes built in for turn on and off the flood coolant. You could hijack those, hook them up to relays on this. There's a relay board in the electronics that has 3 outputs, so you can turn on and off various stuff with code in your generated G code. Among other things, and you can play around with that.
Question.
Anything else? Yes.
The device, the computer that's driving this is not networked, so if you need something, you need a flash drive.
It is.
It is networked now.
You can, the gray wire coming down is our network.
So you
it
can
does.
copy to the drive.
Yes, you can copy off the internet, copy to a drive. There's a, sorry it's not in the best condition currently. There's an extension, a USB extension connected back. Eventually going to have out here so you can pop a thumb drive on this and load your G code or whatever off that. And then probably you can put on some of the basic keying stuff for the G code generation stuff on that, like the DXF to G code and then image to G code utilities. What else? Also, if you're doing NDF, vacuum. Vacuum afterwards. Please clean this thing up.
Yeah, I was going to ask you to think a future upgrade. We can put one of those vacuum shrouds.
We got one that I need to adapt for our particular shop vac that we have over here. But we also have to be able to, well, I need to make the skirt a little bigger because...
So it'll vacuum longer.
Yeah, because right now the bit will be like down here and that's not
It's not really enough.
How does that go on there? I'm kind of curious. How does that thing go on?
The
Like the bit goes through there? Or?
yes, I'd have to move the router up a bit, but this bolts onto the outside on the bolts that go on there.
Okay, yeah, and then you just stick the vacuum.
And then you stick a vacuum in the side.
The shroud would actually make it difficult for you.
Yeah, that's it.
Good overview.
Questions?
Good overview.
Oh, yeah.
I don't know. Probably.
You would need a really good vacuum to safely do that.
Yeah.
The mess you were talking about.
Yeah. Like I said, this, as you're cutting, this will shoot stuff everywhere. So, yeah, it would be really nice if we could have a better method for dealing with that. I think the better one that we came up with was put a gantry here and have a vinyl curtain. Have just like a clear vinyl curtain that goes around this entire thing.
Like they use for welding and stuff like that.
Yeah. So that's probably going to be an upgrade. Currently, the limit switches are a little pokey, so we still have to do a little bit of work on that. We have some more cables. We have to actually hook those up. But it's pretty much operational right now. I have not trimmed it to make sure that the bit is actually on, or the router is actually on there 100% straight.
How do you do that?
You basically use this,
Right.
put it on one of the sections that's going to be flat or perpendicular, or should be perpendicular like the outside of the casing. Move it up, see if it deviates, and then do it for the other axis. And then, stick something in there. So adjust the tilt. If this isn't in here perpendicular to your axis perfectly, as you do this, it's going to be a little bit off. So when you mill out large areas, one side of the cut is going to be a little bit deeper than the other, and it'll be obvious that it's not 100% perpendicular to the surface that you're cutting. With this, you just have to kind of adjust it a bit, maybe find some shims or something to put in there to get it right? That's called training. When you're first getting the tool up and working, and also later on doing maintenance.
Any other questions?
Can it change the Z-axis at the same time as it's traversing X?
You should be able to do all axes at the same time, and I'm pretty sure I've seen it do that when it's done in homing and other operations. It depends on what you put in your G code.
Thank you very much.